Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. Here we are going to conclude the chapter number 3 of microwave engineering, where we have dealt with a family of microwave tubes that have a cross orientation of magnetic field with respect to the direction of electron beam. So in this family we have gone through the understanding of very popular magnetrons working as oscillator. These included the cylindrical, linear, coaxial, inverted coaxial, frequency agile magnetron, and lastly the outgrowths of them, that is the forward wave cross-field amplifier and the backward wave cross-field amplifier. Several problems have also been solved based on to this topic. So let us take the details of this last topic and conclude this chapter. The topic is titled Backward Wave Cross-Field Oscillator. So as we know the difference between basic amplifier and oscillator, so the device is oscillator and the RF wave is to be generated. So in the structural diagram you won't be finding any kind of RF input, only the RF output will be generated by having the interaction of two energies inside the device. So the two energies will be in the form of electron beam that is focused between the two electrodes, and there it will be a signal into the microwave oscillation. So now the backward wave cross-field oscillator is having the two configurations. The first configuration is said to be a linear configuration, and this device is also said to be carcinotron, whereas the second configuration is called as circular carcinotron. So very first of all we shall be understanding the first type, that is linear carcinotron. To understand linear carcinotron we have the structural diagram. So let us get the details. In this diagram, very first of all, the two things that are important to us, that are the electrodes here. So a negatively charged cathode terminal and the positively charged end, that is the collector terminal, are the two important ones, and in between the two there it is the focusing of electron beam. Whatever the devices we have gone so far, there it is somewhat changed with respect to the alignment of these particular electrodes. Now you can see in this diagram, along with these two electrodes we have the presence of slow wave structure also. So here the cathode and the slow wave structure that are parallel to each other. Now as they are parallel to each other, initially the electron will be generated onto the surface of the cathode like this, and if there it is nothing external force regulating the flow of these electrons, it has to travel in the upward direction as far as the page of this particular diagram is concerned. But now there it is the presence of magnetic field. The presence of magnetic field we have denoted here representing capital B, that is magnetic flux density, and as it is having a cross orientation, that means it is perpendicular to the electric field inside the device, we have made a cross sign here, that is inside the plane of the paper here. So here we have electron beam, and because of this particular magnetic field the flow of this electron beam is inclined by the angle of 90 degrees. So initially the electrons used to travel into the upward direction, but now the magnetic flux has tilted it or inclined it with 90 degrees, so that from left hand side to the right hand side the electrons will be moving. At the extreme end we have the collector here. So now the electric field E bar, electric field intensity, is also represented here. The magnetic flux density is also represented. Now along with this cathode end there it is also the existence of sole terminal inside this particular device. See here, V0 is the DC potential between the accelerator and the cathode, whereas V suffix SO is given to the sole and V suffix CO is given to the collector. So collector is at high positive potential here, whereas the RF termination is finally grounded here. Now this is the RF signal that is produced by the procedure of oscillation. So only the oscillating output is taken out of this particular device. Now as we see in this particular structural diagram, we have the electron beam and the slow wave structure. The direction of the electron beam is from left hand side to that of right hand side. So this is the one, whereas the flow of the signal onto the slow wave structure is from right hand towards the left hand side. So I can say that the flow of the signal has a reverse direction with respect to the flow of the electrons in the device here. So this was the structural diagram with respect to the linear carcinotron. Now let us have the help from another diagram where we shall get the working procedure cleared. So here we have the diagram, where in this diagram we have represented the soul portion and the circuit, that is the slow wave structure. So in the passage between the slow wave structure and the soul, the electron beam is focused and it is moving left hand side to right hand side. At the position of A, here the motion of electron is somewhat directed towards the slow wave structure. So this is the direction. When the electrons come to the position B, so that time the velocity of the electron or the direction of the electron is somewhat towards the soul position, which is reverse to that of the earlier case. Now at the position C, it again goes towards the circuit and it has somewhat deviation towards the circuit position or the slow wave structure position. Next to that, at the position D, it has again gone towards the soul position. So this little bit to and fro of the electron motion we find in this particular diagram while the electron beam reaches up to the collector end. So these things go on increasing here. Finally at the position E, the electron have shifted little bit more towards the slow wave structure, that we can notice at the position E, and at the position F the reversal is done, that they have moved towards the position of the soul. Finally at the position G, sometimes it is also a situation that the electrons hit the body of, or they strike the body of the slow wave structure, and finally they end their journey onto the collector terminal here. So this was the simple working procedure of the linear carcinotron. Now we go on to understand the second type of configuration, that is circular carcinotron. The circular carcinotron you can see in this diagram, as compared to the earlier configuration. There it was the linear shapes with respect to the electrodes and the overall body inside the device. Here we have circular dimensions, or you can say the cylindrical dimensions into the three-dimensional case for this configuration here. So here the very important electrode, that is the cathode, that is negatively charged, is shown at this particular place. And now the collector is shown beside it, having such kind of a rod, and it has the RF attenuator that has a circular fashion of orientation, along with the slow wave structure continued with this RF attenuator up to the initial position of the cathode here. As in the before case, we have seen that the direction of the electron beam was tilted by 90 degree. So initially, because of the supply of DC potential, there it will be the generation of free electron onto the body of cathode, and because of the presence of the magnetic field, it will be moved in this particular fashion. So it will be having a circular path followed from the cathode end up to the collector end. In this journey, the electron flow, here it is controlled by grid. Also there it is the existence of accelerating anode to enhance the speed of electrons into the electron beam. Finally, as the interaction between the electron beam, the energy in the electron beam and the slow wave structure is done, we obtain the RF output. So slow wave structure is having a very vital role in the operation of this particular device, so that the oscillation is produced here. Here the representation of electron beam and the RF wave we can notice inside this particular diagram. As compared to the earlier configuration, that is linear carcinotron, the sole terminal is also having circular dimension here. So this was all about the two configurations of the carcinotron, that is the backward wave cross-field oscillator. Now it's time to analyze the working operation of the carcinotron device with the help of mathematical equation. As in the previous topic, there we have gone through the understanding of solutions with respect to the propagation equation. Here the secular equation we set with the help of propagation constants. So very first of all, we set gamma suffix 0 is equal to j times beta. So here beta is the phase shift constant. The setting of gamma suffix 0 is equal to j beta we name by equation number 1. Similarly, we also set the propagation constant gamma is equal to j times k with epsilon. Epsilon being the permittivity of the medium inside this body of the device. So this new equation for gamma we name by equation number 2 here. Now using these two propagation constants, the wave propagation equation with respect to the carcinotron operation we can express into the next equation. The next equation, it will be, onto the left hand side we start with a bracket that has beta square minus k square added with j times twice k epsilon. There in the square bracket we start with j times beta suffix e minus k minus epsilon. The square bracket is completed. Again we have the representation of beta suffix m square minus in the bracket beta suffix e minus k, bracket is squared, minus here we have j times twice of beta suffix e minus k into epsilon. So this is the left hand side, and the right hand side is given as, here we start j times simply the phase shift constant beta into, here we have beta suffix e, k square in the bracket beta suffix e minus k added with twice alpha divided by 1 plus alpha square into beta suffix m, and finally h is squared here. So this is the representation of the equation number 3. So in this equation, as far as the propagation is concerned, whatever it may be the alpha, it accounts for the attenuation, a kind of losses into the propagation. The beta represents the change into the phase while having the propagation, that is very necessary. So beta represents the phase shift constant, and gamma that we have into the equation number 1 and 2 to be the propagation constants here. Now for the device operation, we want the interaction between the two energies inside the device to occur in efficient manner. So for that case, the velocities should be matched between the two energies here. So for that case, to find the solution with respect to the earlier equation, we set here beta is equal to beta suffix e. Beta suffix e is the phase shift constant with respect to the electron beam here, whereas all other representations of the parameter in the earlier equation can be taken from the previous derivation that we have taken commonly for the previous devices of this particular family. Along with beta is equal to beta suffix e, we also take beta suffix e minus k is equal to beta suffix e into small b dash. Small b dash is a very small number, so therefore we can have a neglection of beta dash squares or beta dash into the multiplication of epsilon. So while neglecting such terms, we get modified form of the equation in the simplified way given by twice epsilon in the bracket j times beta suffix e small b dash minus epsilon is equal to beta into beta suffix e small k in the bracket. Here we have v dash divided by beta m squared plus twice alpha divided by 1 plus alpha squared and here finally we have 1 upon beta suffix m into h square. We can further simplify it to the form. So replacing, we make it beta suffix e k into twice alpha divided by 1 plus alpha square beta divided by beta suffix m into h square, or further it can be taken to the form twice beta suffix e k into capital D square. This new representation having the same left hand side, that is twice epsilon in the bracket j times beta e b dash minus epsilon is equal to this one. So this equation is represented in the equation number 4 here. So in this equation, capital D square we have represented. Therefore, capital D square will be given by, in place of alpha divided by 1 plus alpha square, a ratio of beta to the beta suffix m into h square. So this much we have accommodated in place for the D square. So this replacement we also give the equation number 5 it is, along with epsilon to be equal to beta suffix e into capital D into del it will be. Now small b dash can be equal to small b into capital D represented, that we can recover from the equation number 5. So the epsilon represented in terms of the phase shift constant capital D and the del can be given as equation number 6, whereas b dash expressed in terms of small b and capital D can be given the next equation number, that is equation number 7. Now we can express the equation with respect to the del. So it will be del in the bracket del minus j times b is equal to -1, or we can write del square minus j times b into del plus 1 is equal to 0. So let this new equation representing in the form of b and del can be the equation number 8. Now in this situation, reducing the number of waves to 2, we can give two equations corresponding to two propagation constants. The equations will be gamma 1 equal to j times beta suffix e plus small b plus the second term we have beta suffix e capital D into del 1. So this will be equation number 9. And gamma 2, the second propagation constant for the second wave, will be given in terms of j in the bracket beta suffix e plus small b added with beta suffix e into capital D into, here it will be del 2. So this will be the next equation number 10. Now here in both of these equations 9 and 10 we have represented dels here. So the dels that have the roots from the equation number 8 we can take, and therefore we can express del 1 in the form of j times, here it will be b minus, we have square root of b square plus 4 divided by 2, whereas del 2, the second root, can be given and expressed in the form j times b plus square root of b square plus 4 divided by 2. So in both of these representations, there it is the change of only sign. In the expression of del 1 we have negative sign used to find out the one kind of root here, and the second root will be obtained by having the plus sign in the numerator here. Now in this wave propagation inside the device, we can mark the length with respect to the y-axis here. So therefore start of the propagation we can take at y will be equal to 0, whereas the end at which we obtain the output parameters, that we can take at y equal to L here. Therefore at the start, with respect to the DC potential, current and another parameters, we can express the first equation. So it will be V1 of 0 added with V2 of 0 will be equal to complete potential V of 0. The next equation number we give in the sequence, that is equation number 11. Now in the help of del 1 and del 2, we can express V1 of 0 divided by del 1 added with V2 of 0 divided by del 2 will be equal to 0, and this will become the next equation, that is equation number 12. Now taking at the end point, so here we can select y of L. So at y of L, the another parameter we can express for potential, V of 0 is equal to V1 of 0 in multiplication to the exponential here, the exponential for representing gamma 1 into L here, added with the second term, here we have V2 of 0 into the exponential minus gamma 2 into L. By the next line, we can get it into the form where we write V of 0 outside the square bracket, and inside the square bracket we are left with del 1 exponential of minus gamma 1 into L minus, here we have del 2 into the exponential of minus gamma 2 into L. The square bracket is completed, and this is completely divided by the bracket that has a difference of del 1 and del 2. So this equation can be the next equation, equation number 15 here. Now in the representation of the current equation, equation number 15, we have a square bracket onto the right hand side. The square bracket represents the inverse of the gain of the device here, whereas to occur the oscillation here, the square bracket should be equal to 0. So therefore we express del 1 exponential of minus gamma 1 into L equated with the second term portion, that is del 2 into the exponential of minus gamma 2 into L. Let this will be the equation number 16 for the condition of oscillation to occur. The ratio of del 1 to del 2, del 1 divided by del 2 will be given by the exponential of gamma 1 into L minus gamma 2 into L here. So it will be finally the exponential of the square bracket involves the phase shift constant beta suffix e in negation along with capital D L, and inside the parenthesis here we have the difference del 2 minus del 2. So this can be the equation number 17 into the sequence here. Now using the equation number 8 into this derivation, we can express the ratio of dels in the form, we have del 1 divided by del 2 is equal to, in terms of b, we have b minus square root of b square plus 4 divided by b plus square root of b square plus 4. Equation, it will be equation number 18. And also we have the difference of dels, that is del 2 minus del 1 term can be expressed as j times square root of, here we have b square plus 4. That will be the next equation number 19. And finally del 1 divided by del 2, it will be the exponential of, in the bracket, minus j times beta suffix e into capital D into L square root of b square plus 4 it will be, and this will be equation number 20. Now equation number 18 and equation number 20 can only be satisfied when we have small b to be equal to 0, and it will be del 1 equal to minus del 2. Therefore the condition for the equation becomes, it will be twice beta suffix e into capital D into L is equal to twice small n plus 1 times pi here. So in this equation, the equation number we put equation number 21, this small n can be any integer here. So with the definition of small n being integer, we can have the definition of capital N recalled. So for capital N, we have the relation with respect to the phase shift constant beta suffix e into L given in the form 2 pi capital N. Therefore, the oscillation condition we express in the form capital D into capital N. This one is equal to twice N plus 1 divided by 4. So I outline this particular condition, and this particular condition for the oscillation with respect to the current device under study will be very helpful in practicing the next problem here. So we shall be using this particular formulation in the next video to solve a problem based on to the backward wave cross-field oscillator, and we shall be finished with the study of microwave cross-field tubes. So I hope you like these videos, and for more information like this on microwave engineering and another subjects, you can subscribe to Ekeeda channel. Thank you.